the way, these background pictures, they're not just there from Wikipedia or anything. I want to make sure that when you see pretty pictures, you can enjoy them, because these are pretty pictures that were taken for my programs from mainly the Very Large Telescopes in Chile, and sometimes from the Hubble Space Telescope, but I'll point those out to you. This one, for example, is a massive star-forming region in the Large Magellanic Cloud, which is a satellite galaxy to the Milky Way. Okay, so the outline of this talk, which I hope is going to last less than an hour, perhaps more, let's see, is the following. So first of all, we're going to have to talk a little bit about star formation. So how do low mass stars form, and how do massive stars form, and what's the difference between the two, because this is crucial. We also want to understand why massive stars in particular are important. Why is it so important that we study massive stars? And this is not to say that low mass stars are not important. I just want to make the case for my research. I'm then going to talk to you about what it is that I do on a daily basis, a little bit more in depth, but still in brief, and then my journey towards these massive stars. And here in the background is yet a different star-forming region, this time in the Small Magellanic Cloud. Okay, so how and where do stars form? And I'm going to give you a very basic overview of how this process works. If any of this is really too simple, then please do shout at me and tell me off for telling you stuff that you already know, okay? In the background here, this is, by the way, this is a massive star cluster in our own Milky Way. This is Trumpeter 14 in the Carina star-forming complex. And this is just a very zoomed-in portion of a very large mosaic that we obtained a couple of years ago with a very nice instrument on the Very Large Telescope. All right, so stars form in galaxies. I think this is pretty common knowledge in that sense. This particular galaxy should be familiar to some of you in this room. It's NGC 300. It's a galaxy at about 2 megaparsec distance. And you can see it has a nice galactic center, but it also has this sort of fluff around it. You can you probably know that these are the spiral arms of the galaxy. This is where the gas and dust concentrates, and this is exactly where massive stars, but also low mass stars, or where star formation in general happens, right? So if we could zoom in there and perhaps look a little better at these star-forming regions, then you would see a collection along these spiral arms, a collection of glowing regions, glowing bubble-shaped structures. And these are these stellar nurseries. These are the sites of star formation. And the reason they glow, or the reason we see them sort of glowing in this optical image in this case, is because the photons emitted by the stellar populations propagate and ionize the surrounding gas. Right, so stars form in galaxies inside what we call molecular clouds. Okay, in the background here, you see a beautiful infrared color composite image of a large molecular cloud complex in the Milky Way. For example, you can see a sort of bubble-shaped structure here. This is probably where young stars are currently being formed. Here it looks like there is gas and dust being pushed to the sides. There's probably a massive star cluster that is sitting in there. We're not seeing it currently because this is a different wavelength than the optical. So these molecular clouds, what sort of stuff is that, right? You've probably heard about molecular clouds before in some form or another. But just so that we're on the same page, what we mean is sort of concentrations of gas and dust. And the gas is mainly hydrogen, but in the densest and coldest part of these clouds, the hydrogen is in molecular form. So we indicate that by that H sub 2 here. But there's also CO gas, there is some water in some forms, particularly in the form of ices, and other gases. And compounds, but also dust grains. So these are mainly silicates and iron, and they have ice mantles. That's coming from outside. Okay, And so in the densest and coldest regions of these molecular clouds is where star formation can happen. Okay, we need really dense and really cold environments for star formation to ignite. Now, solar mass stars, we think we know pretty well what the sort of general picture is of their formation. And in general, it goes like this. You probably can't tell because of the light in here, but it starts with one of these dark molecular clouds that perhaps has very different concentrations of denser gas. That's what you can't see, but there are darker patches in there. And where the density gets to a certain limit, this dense core can undergo gravitational collapse. And so matter is going to start falling onto that dense patch more and more until the central condensation, if you want, reaches the mass and the temperature enough to call it what we call a protostar. Okay, so a protostar has an accretion disk around it. So around its equator, if you want, it has a sort of a disk structure via which it's continuously accumulating, eating matter. That matter is falling onto the disk from the envelope that is surrounding the star. And because of momentum conservation, we also have this bipolar outflow that shoots out from the poles of the star, which is a consequence of the accretion. Okay? And so later on, the sort of surrounding material will start to disperse. The star is going to evolve onto the main sequence. The leftover of the accretion disk is later going to form the protoplanetary disk, from which, of course, the planets will form. Okay? This is a general picture of low mass star formation. Now, we also have pretty good observational evidence for the various stages. We have observed the various stages of low mass star formation multiple times. So, for example, for the earliest stages where we have these infrared dark clouds, here's an example. This is an infrared image with a dark patch in the middle, and we'd say there is nothing there. That's actually not right. It's just not visible in the infrared. That's why we call it an infrared dark cloud. But if you look at it at longer wavelengths, so towards the radio regime, for example, then you see that actually this dark patch is filled with structure. And these are different gas tracers. So this is a species N2H+, but then there is also SiO. And you see there is different types of structures in these different tracers, but really the takeaway message here is that that seemingly dark patch is filled with cores of dense gas that will eventually, or have already, started to form stars. We also observe jets from young stars. These are really pretty examples. This is perhaps the nicest one. There's a central little star there, and then these beautiful jets that come out to either side of that star. Of course, we also know of famous images like this one from the ALMA telescope in Chile of HL Tau, which is a beautiful image of the protoplanetary disk. Okay, good. Now these were low mass stars, and as I said, we have a pretty good handle on how, on the understanding of how they form. But what about massive stars? And really, I should have defined this before, but with massive stars, I mean those stars that have 8 or more solar masses. Does anybody know why we say 8? Like, what's that threshold about? So, low mass stars and intermediate mass stars, so everything below this sort of very empirical threshold, really, they get to do some hydrogen burning and then perhaps to do some helium burning, but then they progress off the main sequence and they become evolved stars and eventually die if you want to. But high mass stars are hot enough to go on and do further elemental burning stages. Okay, so these are the stars that will produce all the heavy elements in the universe. And for example, carbon burning can only happen in stars larger than 8 solar masses or heavier than 8 solar masses, and that's why we have that sort of threshold. Okay, So now, the formation of massive stars is a bit of a problem, okay? And I'm gonna talk to you about only 2 of the problems, but there are more. Life is never easy. Now, the first problem is, how do massive stars form? Because there's a little thing called radiation pressure problem, and we'll go into that in a second, which really wants to answer the question, how does gravity, how does this gravitational infall of material overcome radiation? And the second question is, why do massive stars form? So where does all of the gas necessary to form these massive stars come from? And that's what we call the gas reservoir problem. All right. So I'm now going to go in reverse order and talk to you first about the gas reservoir. Oh, sorry, that's of course a typo. The gas reservoir problem. Now you'd think that, say, a molecular cloud that has 10,000 solar masses in gas available should easily be able to form a star of 20 solar masses, right? The matter is all there. But unfortunately, that's not really how things go. So the question that we're trying to answer here is, do massive stars form via a single monolithic collapse of a dense region in large clouds, so sort of like a scaled up version of low mass star formation? Unfortunately, that's not really viable, because the star formation efficiency, so the efficiency with which molecular clouds can form stars, is really, really low. Molecular clouds are terrible at forming stars. So only a few percent, if at all, of all of that gas, say 10,000 solar masses, is actually going to end up in stars. And the rest of that gas is going to be dispersed, okay? So even though I have 10 solar masses available, that does not mean whatsoever that it will form a 20 solar mass star. Right, so molecular clouds, takeaway message, are highly inefficient at forming stars. So how can we make this efficiency more efficient? How is it possible that we do observe stars that are so massive? Okay, so we have, I should have checked the talk, of course, before, but we have a couple of solutions to the gas reservoir problem. Apologies for the transitions. So the first solution is what we call core accretion. Okay, so bear with me. Core accretion is simply what I just said before, a scaled up version of low mass star formation. So we have one massive core, one massive dense patch of the molecular cloud that forms one massive star, okay? But of course, for this to be true, we would have to observe these really dense, really massive cores that don't have any stars in them. But the problem is we don't really see these. I'll talk about this in a second. Because the problem is that if you have a really massive core of gas that is just sitting there, it will, unless stopped, want to fragment into tiny little patches and form lots of low mass stars. And so wherever we look, we find lots of low mass stars being formed. We never find these massive cloud cores that don't have any star formation within them. The second solution could be what we call competitive accretion. Now, competitive accretion forms multiple protostars that are a bound collection of stars in a cluster, okay? And now you have to think about potential wells for a second, because if you have a cluster of stars sitting sort of together in a region of space, the combined gravity of these stars is going to make like a potential well, okay? And gas can fall into that potential well. So competitive accretion just means that stars form in clusters, the cluster makes a well, And so that well is going to attract more gas, and the most massive stars are the ones who are going to be able to attract most of that infalling gas. And so they will compete for the accretion of that gas towards the center. Okay, so in the center of that potential well, where the massive stars are forming, is exactly where you will have the higher accretion rates needed to form higher mass stars. Now, there is a problem with this too, of course, and I'm giving a little bit of stuff away here, which is a thing called stellar feedback. So stars will start radiating, they have stellar winds, and all sorts of stuff. They will go supernova, so they will, through this sort of feedback mechanism, disperse the gas and halt the accretion, okay? And if we wanted to think about competitive accretion as a viable option, then observationally speaking, what we would be looking for are signatures of competitive accretion. So we want to look for gas flows that go towards a central star cluster that is still very young and forming. All right. Now, as I said, we are still looking for massive starless cloud cores, which would be an observational signature of the core accretion scenario. We haven't found them yet. But in terms of competitive accretion, there is actually some good news. Whilst we haven't found the smoking gun observational evidence for competitive accretion, we do see that there are regions where stars form. There are these bright blobs in here. This is all stuff where massive star formation is happening. And we see like highways of gas, filaments of gas, indicated here by these purple lanes that go in. And these are gas flows that go towards where these massive star clusters are forming. And so this is not proper competitive accretion, but it is a scenario similar to that. Sometimes it's called the conveyor belt model, but other people have hypothesized the possibility of a so-called hub filament system, such that you will have a central hub, which is fed by filaments. Okay, so the central hub is where the stars are forming, and the filaments are just streams of gas falling onto those hubs. So that's good news. Okay, now back to the first problem, which was why do massive stars form? And that was the radiation pressure problem, if you recall from a couple of slides ago. So the problem here is that massive stars, they will start burning hydrogen while they are still forming. So really, if you want to turn this around to properly understand it, they are still actively accreting matter while they are already on the main sequence. Now, what does this mean? They are still accreting while they burn hydrogen. And burning hydrogen means outputting enormous amounts of radiation. And that radiation, you can imagine, will want to, as it flows out, will also push out everything that tries to fall onto the star. Can you see that in your mind, right? So the gravitational infall, what I sort of colored with these blue arrows here, is halted due to the radiation pressure. And the radiation pressure is there because the star is radiating, because it's burning hydrogen, it's on the main sequence, okay? So in fact, if you equate the gravitational collapse and the radiation pressure, then you'll notice that you cannot form stars more massive than 20 solar masses because of this problem. But we know there are stars that are more massive than that, right? So how can we overcome radiation pressure? How can we continuously bring matter onto a star that is so powerful in radiating stuff away? So one scenario that has been postulated is that of disk accretion. So I showed you earlier that low mass stars, when they form, they will have this accretion disk via which they sort of still gather material. And the same could be true for high mass stars. in such a way that matter can flow onto the star via the accretion disk, and the rest of that powerful radiation is just beamed out from the top and the bottom of the star, if you want. So that disk is somewhat a protection the star has. It's food reservoir, and all the powerful radiation that would be otherwise be destructive is funneled away in different geometries. Okay? And like that, you can form stars up to about 40 solar masses. So good news. The other thing that you could have is mergers. Well, you know, if stars form in clusters, and these clusters are tightly packed, stars could collide, right? You could have a 5 solar mass star and another 5 solar mass star colliding to form a 10 solar mass star. Well, unfortunately, models have shown that for this to be a possible solution, you would need star clusters that are so dense, tend to be 8 stars per square parsec per cubic parsec. This does not perhaps sound like anything too familiar, or you can't really picture it. But trust me, it's a super high stellar density, and it's not really something that we have ever observed. Okay? Not even globular clusters are that densely packed. Also, if you form massive stars via stellar collisions, then the ultimate star cluster that has formed from a molecular cloud will actually not have the right amount of massive stars. It's going to have more massive stars than what we observe to be typically true for star clusters. Okay? So we can rule the second solution out. But you never know. I mean, stellar encounters can still happen. It's a stochastic process. So perhaps that's something that we could observe. Also because we have stars tendentially form in binary systems, and those can potentially attract then another companion. On? Yeah. Okay. Now, titles are again off. Never mind. Actually, this works quite well. So we were talking about the radiation pressure problem, right? And one of the solutions was this disk-mediated formation scenario, where you have the disk, and then the radiation can escape from the poles if you want. So if disk accretion is a potential solution to the formation of massive stars, then arguably we should observe disks around massive stars, and we should observe these jets coming from these young stellar objects, what we call YSOs. Okay, so we should observe these massive young stellar objects with disks and jets, just like we observe for low mass stars. In the background here, you see an artist's impression of what this could look like, although again, the light is a bit silly. Beautiful accretion disk, and then this light cone shining out, that's the gas, and then radiation escaping. Okay. Now, there is some great news, because we do have some evidence for disk accretion going on in massive stars. Okay, so here are a couple of examples of this. So this is the Herbig-Haro HH object 8081. It's a star of about 10 solar masses that is forming in our own galaxy in the Milky Way. Okay, you can see it. The source, the star itself, is sitting up here, but then down here in this image, you see dark patches of fluffy stuff, which is blown up here in a different color scheme. This gas's emission. So this is gas that is glowing. And it's in a direct line from the source, if you want to. And if you look at the source in radio, then what you will see is that the central star is launching a bipolar jet. So this is evidence, observational evidence, for a jet being launched by the source. And what is happening down here, this material there that you see glowing, that is where the jet, so this is a high energy jet, it's hitting interstellar matter. and it's ionizing that interstellar matter. Okay? Right. Here's another example. This is Orion Source 1, also sometimes referred to as the KL object. It's the star that is forming in Orion. It's a young massive star of about 15 solar masses. Okay, and it has. This is an actual image, and this is an artist's impression of this image. So it has this sort of sausage-looking like structure in the middle. That's the accretion disk. And we know it's an accretion disk because if we look at the velocity distribution of the gas in this disk, we realize that it's Keplerian. Okay, the gas is following the Keplerian motion, which means which is smoking gun evidence for the fact that this is an accretion disk and not just like a rotating structure around the star. Right, here's another one. This is a star called AFGL 4176. It's about 12 solar masses. It also has a Keplerian disk. So whenever you see these sort of blue to red maps, these are kinematic maps, so where we show the velocity of an object, and you can see there is this gradient that goes from blue towards red, and then in the middle is where the star is, and the blue and the red is the rotational structure of the disk, right? Stuff that is moving away from you is going to be red shifted, and stuff that is moving towards you is blue shifted. That's why we use those colors. And just in comparison, I showed you the protoplanetary disk of HL Tau before. So this is a low mass star with a protoplanetary disk. And this disk of HL Tau is so tiny in comparison to the enormous Keplerian disk of AFGL. Okay? All right. Now, we actually have recently been able to start observing jets from massive young stars in other galaxies other than our own as well. And that is mainly thanks to the fact that our telescopes and our observatories are getting better and better. We have much higher spatial resolution, so we can observe things that we could previously only observe in the Milky Way at insane distances. And here is an example from my own work. This is yet another of these Herbig-Haro objects, HH 1177. And this is a young star that is forming in the Large Magellanic Cloud. This is a star-forming region, and if you zoom into that star-forming region, you will see a tiny little pillar of gas. This is this little structure there. And you see these kind of like arch-like structures up here and also down there. And those are there because there's a jet. You can see the jet as a blue and red shifted structure here. But you really have to imagine that the star, which is this faint glowing thing up here, is shooting out that jet, which is propagating into the star, into the gas around it. And wherever it hits denser gas, it will sort of do it in a snowplow effect. It will accumulate gas in front of it as it's propagating. That's why we see those arcs there. And this is a star that is about 12 solar masses heavy, and the jet that it's launching is about 11 parsec size. Now keep this number in the back of your mind, because later I'm going to show you a picture of Orion, one of the most famous star-forming regions in the Milky Way. And you'll see that Orion is only about like 0.5 parsec across, and this thing is so much bigger than the entire Orion Nebula. It's ridiculous, okay? So the question now is, do we see a disk associated with this jet? Remember, disks and accretion disks and jet go hand in hand, okay? Actually, perhaps we do. But don't say this to anybody else, because this is really fresh stuff. I have just received a really nice data set from the Atacama Large Millimeter Array, where we do see one of these velocity gradient things I was showing you earlier. So we're hoping that it's Keplerian. Analysis is still ongoing. We'll see. Stay tuned. Okay. So now I've convinced you, hopefully, hopefully that disk accretion and jet launching are observed in massive stars. So a disk accretion is a good possibility for forming stars, at least up to 15 solar masses. We have not observed disks or jets around more massive stars yet. Okay? And now, well, we know that massive stars exist. We know that massive stars up to, hundreds of solar masses exist. And we think that we have sort of started to understand how they form. But why would we want to know about these stars in the first place? Like, why are they important? Why are they interesting? And the key word here is feedback. I've already mentioned feedback before, but let's talk about it a little more, okay? So in a star cluster, massive stars are by far outnumbered. They actually only make up 1% of the stars in the star cluster. So they're pretty rare, okay? But they dominate the energy and the momentum input of that cluster, okay? So if you take one massive star, it will produce more energy and more momentum than all the low mass stars put together, okay? Now, this energy and momentum input from massive stars is what we call feedback. And there are different mechanisms via which massive stars do this feedback thing, okay? So first of all, of course, outflows in jets. As you've seen, these jets, as they propagate through star-forming regions, they tendentially can push away gas as they travel, okay? But radiation pressure is, of course, always present as long as these stars are radiating. Okay, so with radiation pressure, really, I mean photons coming out from the stars, hitting dust particles and imparting momentum to those dust particles, and so pushing aside stuff. Okay, so this is really mechanical interaction. Then, of course, there's ionization. Okay, these high energy photons will hit the gas, ionize the gas. There's stellar winds. Massive stars have really powerful stellar winds, and ultimately they will go boom, right? And supernovae, we know, are amongst the most powerful and destructive events in the universe. So you can see how feedback, it originates on the very small scales of the stars that are responsible for that feedback. But feedback has profound effects up to the scales of entire galaxies, actually. So, right, we see these bubble-shaped structures because the gas is being pushed aside by the massive stars. But even on large scales of entire galaxies, massive stars are the ones that regulate the formation of new generations of stars. By pushing away that gas, by exploding as supernovae, by mixing up everything, they have this effect of regulation, okay? So it's a multi-scale phenomenon. And this is what I meant earlier when I said keep the 11 parsec size jets in mind. This is the Orion Nebula. It's the very center of the Orion Nebula. And as you see here, it's 0.5 parsec across. If you talk light years, then that's 1.6 light years. These are the iconic pillars of creation. I'm sure you've seen these multiple times. I can't go to a conference without seeing at least 2 talks that show an image like this one. But this one is actually one of the ones I've taken with the Very Large Telescope. And these pillars, while huge, are only 1.7 parsec in length, the longest one, right? And just for reference, we are about 8,000 parsec from the center of the Milky Way. So you can see again, like that the jet of 11 parsec is quite substantial. Okay, so this is feedback on small scales. I'm showing this slide really just because of feedback, and I went back to talk about the jet from before. But again, the center, so you can't see the stars here, but there is a massive star cluster there. There are about 4 massive stars that are responsible for evacuating that region, for pushing aside the gas and producing that glowing. These pillars are the shape they are because of stellar feedback. There is a massive cluster sitting somewhere, on the second floor up there. But the radiation from the massive stars and the So the pressure and the photons coming from these massive stars have shaped the surrounding gas into these curious shape structures. And what is happening here is that, say you have a dense pocket of gas within a larger envelope of gas, and you start eroding the gas from the top. So all the fluffy stuff around the dense pocket is going to be pushed back, but the dense pocket is going to somewhat form like a little shield around which then the feedback streams, and that's why we have these pillar-like structures. There are dense pockets of gas sitting at the tips of these stars, shielding the rest of the gas behind them. Okay, and in fact, now you perhaps want to know if these dense pockets of gas form stars at the tip of the pillars. Actually, they do. Many of these pillars have at their tips little stars, low mass stars that are being formed. Okay. On large scales, feedback is also really important, and this is my slide to convince you of that. Now, this is a simulation. It's the same simulation run twice, and this is a simulation of a galaxy that is trying to form stars. Okay, the difference between these two final snapshots of the simulation is the following. Imagine that in your simulation, you have a button which is called stellar feedback, okay? And in the first run of your simulation of the galaxy, of how it evolves and forms stars, you crank that all the way up, you max out the stellar feedback, and the result of that is this blob of gas. It's just sitting there, not really forming many stars at all, okay? While the opposite is true when you turn feedback off completely. So if you do that, then the galaxy is going to form way too many stars and use almost its entire gas reservoir and end up with no gas and having just formed lots of stars. Of course, in reality, galaxies look like something in between, right? They do form stars, but not in a runaway situation. So this is just showcasing the profound effect that feedback can have, okay? So without the stellar feedback, the universe would simply not look like what we observe it to be. And we need to understand what the right feedback recipe is for our galaxy evolution simulations, okay? So in the field of stellar feedback, there are four main open questions, or at least the ones that are the topical ones. The first one is, how does feedback depend on where the massive stars form? Like, does it matter whether a massive star forms in a Milky Way type galaxy or in a large Magellanic Cloud kind of galaxy? Okay. What are the dominant feedback mechanisms? I talked about radiation pressure and supernovae and ionization. Like, are any of those more important than others? What is the role of feedback in actually regulating the formation of new generations of stars? And last but not least, how does this role change? How does feedback affect the small scales and the large scales, so the scales close to the stars and the large galactic scales differently? And all of this is what I work on, okay? Now, there is one little thing that we haven't talked about when it comes to stellar feedback. One mechanism that I haven't mentioned so far, and that is chemical enrichment. So I mentioned already before that massive stars are the ones that produce all the heavy elements as they live. Okay, so when they die, when they explode as supernovae, they will disperse the heavy elements they have formed in their cores into the surrounding interstellar medium. And we call that chemical enrichment. They enrich the surrounding medium with chemical elements, right? So just to put the importance of this chemical enrichment into perspective, I wanted to tell you a very brief story, which is the following, okay? So a long, long time ago, in the very early universe, the dark ages are coming to an end. The first generations of massive stars are exploding as supernovae, so they are dispersing their newly minted heavy metals into into the interstellar medium, okay? And the first molecular clouds are now forming stars and star clusters in the fashion like we understand it today, okay? So for reference, we are here nowadays, but our story really begins after, shortly after the Big Bang, and at the first generation of massive stars. And by the way, the first stars that were formed were all supermassive, okay? Good. Now, besides the energy injection of supernovae as they explode, right, we have already said that we have this dispersal of elements that go into the surrounding interstellar medium. And perhaps these elements will then end up in the accretion disk, which is then going to be the protoplanetary disk, okay, of a low-mass star, perhaps like our sun, that is then eventually going to form planets, maybe planets like our own dear planet Earth, right? So really, what I want to say with this is that you are all, sorry to say so, but nothing but cosmic mud, okay? It's an endless recycling of material. Every atom in here and on you is coming from massive stars. And I think that's pretty poetic, isn't it? All right. Okay, so the conclusions of this first long part of my talk are the following. So massive stars are cool, at least I think they're super cool. I hope that some of you also think they're super cool after today. We really are only starting to understand now how they form and really how they influence the environments they form in. There are lots of many open questions. So, what are the initial conditions? How do we form these beasts that we observe at 40 or 100 or 150 solar masses? And how does exactly this feedback from massive stars work? So that's all interesting stuff that in the next decade or so, I'm really hopeful that we'll find lots of answers to. So first of all, we want to observe disks, accretion disks, and jets from stars that are more massive than those 12 solar masses that we have identified so far. The problem is, of course, massive stars don't live for long, so if you do statistical calculations, finding these objects is going to be increasingly difficult with increased mass. Massive stars are still very much embedded in this dense gas they have formed in, so looking through that gas is really difficult. Low number statistics, as I said earlier, massive stars are rare, so let's see what happens. We want to study this feedback thing with observations because that will really help us to better constrain simulations, and therefore if we have better and better simulations, we can make better predictions about the universe. We can make simulations that are closer to reality, which would be awesome. We can also then inform how to build the next generations of telescopes and instruments, okay, to increasing higher spatial resolution and sensitivity, and so on and so forth. Okay. Now, just real brief, we started at 10 minutes late, so I'm going to take 10 minutes more if that's fine. So just very brief, what is it actually that I work on? Because of course I don't. The first part was more lecture style than anything. Okay. So this is a very nice bubble chart of my daily business. So feedback from massive stars is sort of the central theme that brings everything together. These lovely people here in the four corners are my awesome research group. And all of these blue things are scientific topics that I'm very interested in. So there are shocks. I haven't really talked about shocks, but when feedback from massive stars interacts with the environment, we have shocks, cosmic shocks. I have done a lot of work on the Magellanic Clouds, so our two nearest neighbor galaxies. They're satellites of the Milky Way. And I have a level 4 student, Eve, who's working on beautiful data of the small Magellanic Cloud. As I said, I work on jets and outflows. I'm really interested in dwarf starburst galaxies. So these galaxies are not your typical spiral arm galaxy. These are much smaller, much less massive than Milky Way type galaxies, but they produce stars at insane rates. And so we really need to understand what is happening and how is star formation different in these really extreme environments. And so Lucy, my other level 4 student, she is working on dwarf starburst galaxies with me. In general, I'm interested in nearby galaxies because these offer valuable insight in lots of different stuff. And so my PhD student, Will, is doing research on that. I started out working on the Milky Way, but I'm sort of increasingly getting to know more of the more distant universe as time goes by. And then a crucial part is this comparison between the observations and the simulations. And I have a master's by a research student, Margarita, who is working together with people who simulate galaxies to compare observations and simulations. I really, really like doing outreach as well, and never mind what this IFU club is. Once you are level 4 students and you perhaps want to work with me, then you're gonna understand what that is, but it's not irrelevant for now. So just real quick about one of these things, nearby galaxies. I've talked about NGC 300 before, so this is one of these nearby galaxies, and it turns out that despite the fact that it's really far away, we now have the technology and the techniques to study individual massive stars, even at distances of a few megaparsecs, and megaparsec distance is proper far away, okay? And so all of this stuff in here are star clusters and gas, but if we zoom in with the right technology, we can go and identify individual stars, like we do in the Milky Way. And this is really powerful because we can do it for entire nearby galaxies rather than just one puny star-forming region at a time like we do here in the Milky Way, okay? So this gray text box is just to say that we have the technology to do this for hundreds of nearby galaxies now, which is super cool. Okay. The other thing I wanted to talk to you about real quick is outreach. So we're currently organizing an event called Durham Astronomy Girls Day. So this is specifically targeting schoolgirls aged 11 to 15-ish from underprivileged areas around County Durham, okay? Because it's really important to make sure that we increase diversity in our field. You can already tell by the audience sitting here that there aren't many girls. And I'm sorry to say so, guys, but it is something really important to invest in because the diversity will lead to the major discoveries of the next century, okay? And so we wanted to organize this for February 11th this year. Obviously not going to happen, but this is International Day of Women and Girls in Science. We're probably going to have to postpone it to the summer, but then it's going to be a yearly event from this year on. And the aim is to bring the girls here for a day, make them just spend the day with us and listen to talks, be able to talk to scientists and astronomers, go around to some lab visits, and hands-on activities. We will want them to observe with telescopes and have a look at the sun through solar telescopes, and all of these kind of things. So if any of you is interested in helping out with this event, please do let me know. Okay, and the last couple of minutes, and then I swear I'm done. Just real brief, how did I get here? Okay, because diverse stories do matter. Okay, so the key message I would like you to take away is that sometimes getting to where you want to go is not entirely a straight route, and sometimes you don't really know what you want to do until a bit later. So you zigzag through life, that's fine. So when I was finishing high school, I was super into emergency medicine, and that's exactly what I wanted to do. At the time, it seems ages ago, but there was this TV series called ER on TV, and I was totally into it. So what it did was a degree in nursing. Okay. Don't ask me to save your life because I have forgotten everything about that. So at this point, but I do have a degree in nursing. But it was pretty clear from day one of that degree that while it's a very inspiring job to be in, it was just not stimulating intellectually enough for me. So I decided to finish it because it's good to finish things. But then immediately after that, I went on to follow my second passion, which then became my first passion, which is astronomy. So much like perhaps some of you, I started out looking, through amateur telescopes. And I think the day that I saw Jupiter with 4 of its moons there was mind-blowing, and I decided that's it, that's what I want to do. I'm going to finish nursing school, and then after that I'm going to go and study physics, because I realized that to become an astronomer I have to study physics. So that's what I did. I went to Munich in Germany, where I did my undergrads, then I went to the Netherlands, where I did my master's, then I went back to Germany, where I did my PhD. But unfortunately, after my PhD, I had to leave academia for a while, okay? So I graduated cum laude, magna cum laude actually, but then I had to move to New Zealand for family reasons. And in New Zealand, there was not a job in astronomy for me because it's a tiny country with not a lot of money for research, okay? Especially not for postdocs. And so I worked as a software engineer for half a year until I decided that that job is not for me. It was utterly boring and super frustrating, and I was still very sad about the fact that I had to leave academia. So in the meantime, I had applied for a fellowship. So I had asked the New Zealand government to give me an insane amount of money to do my research, and they said yes. And so I managed to get back into research, but I mean, really, I lucked out so much, right? But that one fellowship really kickstarted my career, because after that I went on to get another prestigious fellowship at the University of California in Berkeley, and where I was sponsored by NASA. And then I ultimately ended up here 1.5 years ago. Okay, so again, I don't want to glorify my success. I just want really to transmit the fact that we all have different stories, and life sometimes does not go the way we want to, but it's okay, and you can change your mind. It's never too late to do something else. Okay, and also it might take you to live and see lots of different places, and I've had the luck so far, of course, COVID-19, before that, to travel quite a bit. I've lived in many countries, and I've visited many more. And yeah, and that's me. So if you can't find me in my office, I'm probably somewhere on a hill or on a mountain snowboarding or running somewhere or spending time with my family, because that's another thing that I haven't mentioned is that when I finished my master's, I had my first child, and just 2 months before defending my PhD thesis, I had my second child. Okay. All right, and that's all from me. So thank you so much for coming by and for your attention, and the floor is now open for questions. Any questions? Or was this way too overwhelming?
You mentioned the very first stars.
Yeah.
How is their formation? Is their formation any similar to the more modern massive stars, or is it not really known yet?
So we don't really know, because we can't study individual stars at those very high redshifts, so at the very early universe. But what we do know is that the very first generation of stars was mostly really, really massive beasts. So we didn't have any low mass star formation at all, right? Which we can talk about offline if you want to, but it has different reasons. Yeah. Yeah. More questions? Sure.
When you go about the accretion disks,
Yeah.
like, what is it that makes one like Keplerian? So I couldn't really follow it after.
Okay, so there is a distinction between. All right, let's take it from the top. Stuff in the universe rotates. Okay, so Earth rotates, and we rotate around the sun, and the solar system rotates around the center of the Milky Way, and so on and so forth. Now, there is a distinction between disks that are proper Keplerian, such that so that the motion is described by the Keplerian equations. And what that does is that the matter spirals inwards,
Right.
okay, and is able to follow to the star, which is different from simply rotating structures around stars, because we see those too, but those don't funnel material to the star.
Right. So the motion of like Earth around the sun would get very.
Yeah, so those are
Right.
just circular orbits
Yeah.
of stuff around the star, but the material doesn't spiral
Oh,
inwards.
right. Thank you.
More questions? Yeah. Yeah.
How do the jets equal out momentum?
That's a very good question. So the stuff that falls onto the star has some, form of energy associated with it, which the star needs to get rid of. In fact, if you can simulate how the accretion disk around the star, and you will have jets almost forming automatically out of that. It's a complicated process, and I'm sure that this is something that you will learn in one of your Astro courses if you're taking those. Again, it's a longer discussion, and I'm happy to have it, but I don't think that this is the setting. But it's conservation of angular momentum, if you want. Yeah.
Touching on your point about diverse career paths.
Yeah.
If someone is considering to go into industry, like myself, I want to go into industry for a few years and then consider a PhD after a couple of years, how could I maintain my physics knowledge or still be able to put a successful application in without the career kind of, it's easy to forget the stuff you've done.
Yeah.
And especially if that career isn't directly in physics. So how can you still maintain that?
So, so there are a couple of aspects to your question. So first of all, if you do want to take time off and then come back, doing it at the end of your undergrad is the best time to do it, okay? Because then you can very well apply for PhD positions. And at that point, if you don't have publication to your record, that's absolutely fine. Most people apply for PhD positions and have not written a paper yet, okay? It is slightly more difficult to go out of academia when you finish your PhD and then try and come back for a postdoc position, because when you apply for postdocs, people will be looking at your publication record, and if you don't have any papers, or if you have very few, people will frown, upon that for the wrong reasons. I'm not saying that looking for high publication records is the right thing to do. It's absolutely not. It's horrendous, but unfortunately, it's how it happens. So I think you can very well spend a couple of years doing something else, and then if you want to, you can totally come back and apply for a PhD. I've seen people apply for their PhD position successfully and doing their PhDs after they retired from their job they've been doing for 40 years. Okay, so that's good news. Of course, you want to sort of stay in tune with what is happening, especially if you already have an interest in a specific field, right? Say that you do your level 4 project or your master's research project with somebody who is working on, simulations of large-scale structures in the universe, okay? Then perhaps what you will want to do is just keep up with the literature, right? You will know where to find daily papers and try and just keep up with what the field is doing, such that when you do come back, you don't have too much to look up anymore. But you don't forget really about physics. You just have to get back into it. It's like riding a bicycle. All right. More questions? No? Great. Well, you can always, if there's interest or if you just want to chat, my office is just across the street, 120 in OCW. Feel free to come by anytime you want. Thanks again for coming.